Shall we start on time as well? All right, everybody, welcome back. And I'd like to welcome, for a second time today, Dr. Jesse Christiansen from CalTech, the NASA Exoplanet Institute, where, oh gosh, how long have you been studying exoplanets there? It's been 13 years of exoplanet research. So we have an absolute expert here with us today to talk about the search for Earth 2.0. And Jesse, please, thank you. Enlighten us and tell us all about it. This is amazing.
Thank you so much, Dr. Reitzel. Hi, everybody. All right, welcome back. So I'm just going to piggyback on what Representative Chu said about how this is such an excellent place. Pasadena is also known as the city of astronomy. I would advocate that it could be the city of exoplanets because the NASA Exploration Program office is here. Did you know the most successful woman planet hunter in the world is here in Pasadena? It's me. So anyway, I'm Jesse Christiansen. I am the chief scientist at the NASA Exoplanet Science Institute, which is just down the road at CalTech. And I am delighted to be here today to talk to you about how we're searching for Earth 2.0. Okay, so let's take 2 steps back and make sure everyone's on the same page because there's some younger folks in the audience, which is super great. Hi, everyone. What is an exoplanet? So this is a graphic, not to scale, of the planets in our solar system. We have 1 star. We have 8 planets. Boo! I know, I wasn't there when they voted. Anyway, but guys, if it's any consolation, Pluto went from being the worst planet to the best dwarf planet. Yay! We've invented a whole new bucket just for Pluto and its friends. And so Pluto said, Namake Maki, you might have heard of these. This was the whole bunch of new objects we found that made us think that maybe Pluto was different from all the rest of the planets and deserved to be king of its own bucket instead of just the worst planet. We also have minor planets in the solar system. That's everything else in the solar system that we've been able to catalog that's bigger than a grain of dust. We have found over 1 million things out there. And there are dwarf planets, asteroids, Trojans, centaurs, Kuiper Belt objects. There's a bunch of stuff out there. So what are exoplanets? Exoplanets are planets around other stars. I'm going to talk you a little through the history of why we thought these existed. Now, for thousands of years, we've had this wandering, which is a cosmology of the sky, right? These original stories of how our stories are in the sky. So the oldest stories we have from the dawn of oral tradition are about the sky. Now, let's talk about exoplanets. So 2,500 years ago, the Greek philosophers, this is the Plato and Aristotle's, were thinking about this. We're like, is there one Earth or many Earths? And they actually argued that Earth was unique, that there would be no other Earths, there was only one. Now, interestingly, when they were talking about this in their very Greek philosopher way, it was very hypothetical, right? It was just a thought experiment. They were just like, what if? Which was their way of doing things, right? Let's just toss an idea around and see what happens. But thousands of years ago, we were asking the question, are there other Earths? Okay, let's fast forward. In 1592, this is the Italian, this is the Renaissance, which is like music, art, literature in the 16th century. This is in Italy, which was one of the centers of this Renaissance, this incredible explosion in science and art and math. And there was an Italian mathematician, Giordano Bruno. And he has this quote: "There are countless suns and countless Earths, all rotating around their suns in exactly the same way as the 7 planets of our system." It's 1592 in this quote, so I'll leave it as an exercise for the reader, which were the 7 planets that he was talking about. You might be surprised. Okay, so Giordano Bruno was out there like, there are planets. Now, he actually also hit on the problem, which is that stars are really bright. We live in Southern California. We are good friends with the sun. It is very bright, especially in July. And planets are very small and faint. So when you look at the sky and you see thousands and thousands of points of light, the planets around those points of light are so hard to find. But he was like, look, they're out there. I believe. Okay, let's jump forward another 400 years into the last century, 1952. This was a Russian-American astronomer, Otto Struve, and he comes up with an idea of how we might actually be able to detect these things. We knew how to see two stars orbiting each other by their velocities. We could measure their speeds. And he was like, okay, what if we take one of those stars out and instead put a big planet there? Could we still see it? Could we still see this star moving because it was being pulled by the planet? So this paper languished. And this happens in science sometimes. Someone publishes a really good idea, but nobody really recognizes what it is for a long time. So between 1952 and 1995, this paper has 7 citations, which means other people thought it was worth talking about 7 times, which is not a lot. And then something happened, which was that in 1995, a pair of Swiss astronomers using this technique that Otto Struve had suggested 40 years earlier, finally found the first planet, 51 Pegasus b, orbiting a sun-like star. So Dr. Reitzel mentioned earlier in 1992, we found some planets around pulsars. That was kind of a weird glitch. They weren't even looking for planets. It was just like, what is that? But we were really looking for planets around stars like the sun. So in 1995, this first planet was found. And in 2019, that pair of Swiss astronomers were awarded the Nobel Prize for this discovery. Now that paper has hundreds of citations in the last 30 years. Okay, so 1995 was 30 years ago. It's the 30th year. It's a big year this year for exoplanets. What's happened since then? All right, I'm going to start this movie. We're going to see what happens. You see the year ticking up at the top. Every time we find a new planet, you'll hear a note and a circle will appear on the screen. You guys have this screen? Good, good. The different color of the circle is how we found it. Now there are more like 10 different ways we can find planets. And you can see as we start to get to the 2000s, the speed picks up that we're finding these planets at. More and more telescopes come online. More and more instruments are trying to do this exciting thing. In 2009, the Kepler telescope launches, which was NASA's first big foray into finding exoplanets. And those spikes that you saw in Dr. Reitzel's talk earlier, those were big Kepler data releases. So this is the Kepler field here, which has thousands of known planets in it now. You can see we're accelerating. The cacophony is increasing. And then in 2022, we hit this major milestone of 5,000 known planets. So NASA had this animation commissioned in 2022 for this big milestone of finding 5,000. So after 2,500 years of thinking about whether there were other planets out there, in particular other Earths, we've gone from none to 5,000 in just 30 years, which is incredibly exciting. And in fact, we think we're actually at 5,933. That's part of my day job is to keep track. It's not just a random fact, I know. We think in about 2 months we'll hit 6,000 known planets, which is pretty exciting. Okay, so, but that's a bunch of planets. What did we actually find? What do they look like? Are any of them like Earth? All right, so this is a plot. There's only going to be one plot in the talk, so stick with me. We'll work through it. It's going to be fine. On the x-axis, this axis here, is how far away the planet is from the star in terms of how long it takes to go around, its orbital period. So our orbital period is 365 days. That's a year. So that's out here, 365. The y-axis is how big the planet is relative to the Earth. So Earth is here at 1. So if you go to 1 and then 365 days, that's the Earth on this plot. And these other 3 squares are Mercury, Venus, Earth, and Mars. So that's what our solar system planets look like on this plot. So before Kepler, this is basically what we'd found. They look completely different from the planets of our solar system. They're huge. These are all Jupiter-sized planets. Jupiter is 11 times the size of Earth. So these are all Jupiter and bigger than the biggest planet in our solar system. And they're all incredibly close to their star. Look at this, guys. This is just days. 1 day, 2 day, 3 day, 4 days. These all orbit their star in just a handful of days. So you basically take a Jupiter and you park it right next to the star. And it orbits in just a few days. So Mercury, which is the closest planet in our solar system, has a period of 88 days. So these are planets so much closer to their star than our planets that it broke how we understood how planets form. Everything we knew about how to make planets was designed to recreate our solar system. And literally the first 100 planets we found looked nothing like our solar system. But it's good job security for a theorist, right? You're like, all right, throw that one in the bin. Let's start again. How do we make these Jupiters right next to the star? So it's very exciting, but it's not very much like Earth. So Kepler was actually designed to find Earth-like planets. And this is what's happened since then. You can see that we've really filled in this space between hot Jupiters. They're Jupiters that are heated up to thousands of degrees, and astronomers shouldn't be allowed to name things. So they're called hot Jupiters, and solar system planets. But you'll notice we didn't actually hit the solar system planets yet. Okay, so we're back to this question of Earth 2.0. I'll start by saying, for me, and this is contentious among scientists, other people today might have different opinions, Earth 2.0 is a rocky planet in the habitable zone, so the right distance from the star to have liquid water on the surface if it has an atmosphere, of a sun-like star. 3 criteria: rocky planet that's the right temperature around a sun-like star. Okay? It's important to define that because people have different ideas, and we'll talk a little bit about that. So this was Kepler. This was our chance. This was our opportunity. Launched in 2009. It's a 1-meter telescope that spent 4 years staring at that little patch of sky that I showed you, that little purple patch that ended up having thousands of planets. This was the patch of sky again, so it's actually very visible from summer in the northern hemisphere. If you guys go outside tonight and look up, if you can find the Swan, Cygnus, and move a little bit towards Vega, which is a very bright star, you're looking at the patch of sky that we know the most about in terms of planets. We know of thousands of planets in this patch of sky. Okay, so the way Kepler finds planets, it's not the way that Otto Struve mainly talked about in his paper, which is this radial velocity method, measuring the velocity of the star. This paper, it drives me crazy. There's a paragraph at the end of this paper where he's like, also, I guess if the planets passed in front of the star, they'd block some of the light, and maybe you could see that too. I don't know. And it's just like, okay. So this is now the most successful method of finding planets, called the transit method. I love how it's almost essentially a footnote in this 1952 paper. So this is an animation of 7 rocky planets orbiting the star TRAPPIST-1. So TRAPPIST-1 is a very small, cool red star that is basically as small as you could be and creditably call yourself a star. If it was any smaller, it would be a brown dwarf, but it just squeaks in. And it has 7 rocky planets around it. Now, normally we'd have no way of seeing these planets, except we're very lucky. And this planetary system is lined up just right. So from our point of view, all 7 planets pass between us and the star as they orbit the star. So this animation at the top is showing what's happening as a planet goes in front of the star, like that. This is real Spitzer data at the bottom. This was something like 500 hours of Spitzer data, Spitzer Space Telescope. And so you were measuring the brightness of the star with time. And when a planet goes in front, you see a dip. And then another planet, another dip. And that's blocking the light. This is the simplest measurement we can make of stars in the sky, how bright they are, right? This is one of the oldest types of astronomy we have. But the precision you need to be able to do it at to see these tiny planets, that's what we needed to do from space. We had to launch a 1-meter telescope into space to see these things. So you can see the distance, the time between 2 transits of one planet, let's say planet B, that's how long it takes that planet to orbit the star. So if you were an alien civilization looking at the Earth and you were lined up just right, every 365 days, you'd see a dip. Now, let me get it going again so I can show you the depth. Here. Yes. The other piece of information you get is the depth of the dip, right? The bigger the planet, the more light it's going to block, and it's going to make a deeper dip. So you can see there's actually different depths of dip here. So it's an incredibly simple measurement, but already you know how big the planet is, what its temperature is, and how far away from the star it is. And you know something about the star. This one's an M dwarf, so you know how bright it is. So now you start to know, are these planets in the habitable zone? So 3 of these 7 planets are in the habitable zone. So let's check. They're all rocky. 3 of them are in the habitable zone, but they're not orbiting a sun-like star. TRAPPIST-1 is a very, very different kind of star. And in particular, what you'll see occasionally, the eagle-eyed among you, I'll ask the kids if they can see it, sometimes the star does something else, which is annoying. Go back and show you one more time. Sometimes instead of going down, You can see the data go up. That's because the star is flaring, right? So when we get coronal mass ejections here from our sun, we get beautiful aurora and some static in our communication satellites. If you're around an M dwarf and you're close enough to be in the habitable zone, these flares are happening all the time and much more energetically than they're happening on our sun. So we actually don't know how big a problem that is. But we know on Earth it's not great, and that our magnetic field is very important for deflecting all of this high energy radiation and particles away from us and making a beautiful aurora, but most importantly, keeping us safe, right? So M dwarfs are putting out a lot of radiation as UV and X-ray. Now, UV is the reason why we're in Southern California, we wear sunscreen. X-ray is the reason why at the dentist they put the lead apron over you when they're taking a measurement of your teeth, right? They're bad. X-rays and UV are bad for life. We use UV to sterilize equipment. So we don't know if rocky planets in the habitable zones of M dwarfs are actually habitable. Okay, let's move on. Okay, so we have found thousands of planets. How close did we get to an Earth-like planet? This is Kepler 452b. I'll stop for a second and say I'm really sorry. They all have rubbish names. It's so cool that we're finding new planets around other stars, and then we call them Kepler 452b. That's on us. Again, we should not be allowed to name things. So it was found by Kepler, which is why it starts with Kepler. It's the 452nd system found by Kepler, and it's the first planet in that system, which gives you the B. The second planet would be C. The third planet would be D. The star is assumed to be A. This is a convention that we inherited from binary stars. Kepler 452b. Okay, let's go through these criteria. It's a little big. It's about 1.6 times the size of the Earth, and that's where we start to get not sure whether it's rocky, like a big rock, whether we just scaled up Earth, or if it's a mini Neptune, like you took one of our ice giants and scaled it down, or whether it's another type of planet we don't have in our solar system. And one suggestion is a water world. A lot of the planets that are in this kind of intermediate size range have a density that's kind of similar to water, like bulk water. Like 50% of these planets could just be a deep water ocean. But we don't know if it's a rocky planet. We think it's got about a 50-50 chance. Second criteria, it is in the habitable zone. This has a period of 372 days. 365, 372, not too bad. And it is orbiting a sun-like star. Okay, so we've got like 2.5 out of 3. That's very exciting. This is honestly as close as we've gotten. The main problem with Kepler 452b is that it might not be there. The data aren't great, guys. It's really noisy. They're a very low signal to noise. And unfortunately, the period of the Kepler spacecraft going around the sun is also 372 days. And when you have something in your instrumentation which has the same period as the most exciting signal that you found, it's not great. It doesn't feel good. There's quite a reasonable chance that there's something introduced by temperature changes on the spacecraft that's created a noise signal that looks like this. So again, we give it about a 50-50 chance of being real. So if it's real and if it's rocky, it's the best chance we have. Do you have a question? Yes. Yes, so this is an artist animation that's entirely made up. We don't know anything about it, except its bulk size and its temperature. So we have a bunch of incredible scientific artists at CalTech, at JPL, at NASA Ames, where this one was done. And their job is to take this little bit of information that we know and the information we know from the planets in our solar system and imagine something new that might not be scientifically incorrect, but that is kind of, extrapolating, filling in some gaps. So we don't actually have, everything I'm showing here is all artist's imagination of what this could look like. So we don't know if there's clouds. We also don't know if there's an atmosphere. We don't know much. But this is the best we have, Kepler 452b. So let's come back to the second best. So I talked about rocky planets in the habitable zones of M dwarfs. Those we have found more of. This is an example. This is the closest star to us, Proxima Centauri. So if you leave our solar system, the first star system you get to is the Alpha Centauri system. So that's Alpha Centauri A and B, which are actually solar type stars, sun-like stars. They're off in the background in this image. And they're orbited at quite a distance by Proxima Centauri, which is one of these M dwarfs. And around Proxima Centauri, using the radial velocity method, measuring the velocity of the star, we have found a rocky planet in the habitable zone. That's kind of unreal, guys. Literally the first star you get to after you leave Earth and the sun is the first, after you leave our solar system, is a rocky planet in the habitable zone. Like, that's where we would go if we needed to borrow a cup of sugar, right? It's right there. The question is, we don't know if these planets are habitable. So we have found 14 so far, rocky planets in the habitable zones of M dwarfs. We don't know if any of them are habitable, but we have a plan. So this is the scariest thing that has ever happened to any astronomer in the history of astronomy. This is the